In this video, we're going to talk about capacitors in series and parallel. And we're going to go over some equations that you need to know and work on some problems. So let's say if we have a battery attached to two capacitors in parallel. Let's say the two capacitors are parallel to each other. And let's use a 10-volt battery. Let's call the first capacitor C1 and the second one C2. Let's say the first capacitor has a value of 100 microfarads. The second capacitor has a value of 200 microfarads. What is the equivalent capacitance of this circuit? For parallel circuits, the equivalent capacitance is simply the sum of all the capacitors connected in parallel. So it's 100 plus 200, it's 300 microfarads. And that's all you need to do to find the equivalent capacitance. Now, how much charge is stored in C1? To calculate the charge, Q1 is equal to C1 times V1. So you need to know the voltage across C1. In a parallel circuit, the voltage across every element that's parallel to one another is the same. C1 is connected directly across the battery, so it has a voltage of 10 volts when it's fully charged. And the same is true for C2. They will all have the same voltage. So V1 is 10 and V2 is 10. So now we can calculate Q1. So it's going to be C1, which is 100 microfarads, or 100 times 10 to the minus 6, micros 10 to the minus 6. And V1 is just 10. So Q1 is about 0.001 coulombs. That's the unit of electric charge. Now what about C2? What is the charge stored on C2? So we can use this equation. Q2 is equal to C2 times V2. So that's 200 times 10 to the minus 6 times 10 volts. So it's going to store twice the amount of charge compared to C1. So it's 0.002 coulombs. The total charge stored in this network is basically Q1 plus Q2. So it's 0.001 plus 0.002. So it's 0.003 coulombs. You can also find the total charge by taking the equivalent capacitance and multiplying it by the voltage. So 300 times 10 to the minus 6 multiplied by 10 will also give you 0.003. So that's another thing to keep in mind. Now, how can we calculate the energy stored in C1? What is the electric potential energy stored in that capacitor? One equation that you can use is this one. It's 1/2 CV squared. So it's 1/2 times 100 times 10 to the minus 6, that's the capacitance, times the voltage across that capacitor, which is 10, and don't forget to square it. So this is equal to 0.005 joules, which we could say it's about 5 millijoules. Now what if we have a capacitor circuit in series? Let's use 3 capacitors instead of 2. So on the left we have a battery. You can see the two different sides of a battery. And let's say the battery's voltage is 50 volts. Let's call this capacitor C1, C2, and C3. Let's say C1 has a capacitance of, let's use large values. Let's say C1 is 2 farads, C2 is going to be 3 farads, and C3 is going to be 5 farads. Now typically most capacitors, they're in a range of microfarads. Supercapacitors have this much capacitance, but just for the sake of simplicity, we'll use these numbers. What is the equivalent capacitance in this circuit? That's the first thing you want to look for. A simple way to find the equivalent capacitance in a series circuit, it's going to be 1 over C1 plus 1 over C2 plus 1 over C3. All raised to the minus 1. So it's 1 over 2 plus 1 over 3 plus 1 over 5. And just type this in exactly the way you see it in your calculator. So the equivalent capacitance is about 0.9677 farads. Now with this information, how can you find a voltage across each of the capacitors? Sometimes you may need to find a voltage of just one of the capacitors, and then with that you can find how much potential energy is stored in that capacitor. But let's focus on finding the voltage of each. So once you have the equivalent capacitance, the next thing you need to do is calculate the charge. Now, there's some differences you need to know between a series and parallel circuit for capacitors. In a parallel circuit, the voltage across each capacitor is the same. It's equal to the battery's voltage. In a series circuit, the voltages across each capacitor will be different if the capacitance is different. Now, in a series circuit, the charge stored on each capacitor is the same. In a parallel circuit, the voltage across each capacitor is the same. Make sure you understand that difference. So once we find Q, this Q will be the same as Q1, Q2, Q3. They all equal each other. And this will be very helpful in calculating V1, V2, and V3. So let's find Q. It's equal to the equivalent capacitance times the total voltage, or the voltage of the battery, which is 50 volts. So 0.9677 times 50, that's equal to, I'm going to write it over here, 48.39. And that's a rounded answer. So that's the total charge, which is the charge on each capacitor, which are the same. So now let's find V1. V1 is going to be Q1 over C1. So take the charge and divide it by the capacitance. Now if you have microfarads, make sure to add the 10 to the minus 6 when dealing with your calculations. In this video, I just got to divide it by 2 since it's in farads. So 48.39 divided by 2 is about 24.2 if we round it to the nearest tenth. So that's the voltage across C1. Now to find the voltage across C2, it's going to be Q2 divided by C2. Q1 and Q2, they're both equal to Q. So it's going to be 48.39 divided by 3. And then that is equal to 16.1. Now to find C3, it's going to be Q3 divided by C3. To find V3. So V3 is going to be 48.39 divided by 5. And that's about 9.7 volts. Now, let's clear away a few things. Now notice that the total voltage is equal to V1 plus V2 plus V3. V1 is 24.2, V2 is 16.1, V3 is 9.7. So if you add these values, you should get 50 volts, which is equal to the voltage of the battery. That's how you know if your answer is correct. It has to agree with one another. The sum of these three values has to equal the battery's voltage. Now let's calculate the potential energy of C2. It's going to be 1/2 CV squared. Now that we have the voltage, we can find the potential energy. So the capacitance is 3 farads. The voltage across it is 16.1. And so this is equal to 388.8 joules. And so that's it for this video.